Hello everybody and welcome to this chemistry video about electronegativity and polarity. In this video we'll be taking a look at covalent bonds and their nature. Then we're going to look at electronegativity, both in terms of what that actually is and what patterns there are in electronegativity in the periodic table. And then we're going to take a look at how polarity can lead to polar bonds and polar molecules. Simple molecules are formed when non-metal atoms share pairs of electrons, typically one pair of electrons, in order to achieve a full outer energy level of electrons. Typically this will be either 2 electrons for a period 1 element or 8 electrons for most of the rest. But sometimes it can actually be 10 or even 12 electrons in the outer energy level. And we can show this covalent bonding in one of 3 ways. The first is where we simply show a stick, and this represents the shared pair of electrons between the 2 atoms. Or we can show the actual energy level itself with this simple circle model, and a bigger circle is usually reserved for a bigger element. And you've got the 2 electrons involved in the bonding shown clearly, and then the 3 lone pairs around the other atom shown here. And then the third way is very much like the second way, except we don't show the actual energy levels, just the electron pairs themselves. It's going to be useful to take a look at how bonds actually form before we can understand their nature more deeply. So if we consider 2 atoms X and Y, we know that their electrons are going to be found in orbitals around this atom. And when a bond forms between X and Y, what happens is their orbitals overlap, and the electron that was in each of their individual orbitals now joins with the other electron and forms a bond, which we're showing here as sort of looking like an ellipse between these 2 atoms. And this pair of electrons is somewhere within this area. And this type of bond, where the orbitals have overlapped end to end, is referred to as a sigma bond, which is helpful because a sigma bond is the equivalent of a single covalent bond. There is another type of bond, which is called a pi bond, which is where orbitals overlap side by side, and this is how a double bond can form within molecules. For this video, we're just going to be focusing on the electron arrangement within the sigma bond. When the covalent bond is between 2 atoms of the same element that are sharing that pair of electrons, then that pair of electrons will be shared perfectly equally, and we will get a sigma bond that is totally symmetrical between these 2 atoms. However, if the covalent bond is between 2 different atoms, we can end up with a very large imbalance between where we find the electrons in the space between the 2 atoms. It can be that the electrons are much closer to one of the 2 atoms than the other. And the reason that this happens is that one of the atoms in the covalent bond, in this case the chlorine, is much better at attracting electrons towards itself from within that covalent bond. It's sort of having a tug of war with the hydrogen atom for the electrons, and it's definitely got the upper hand. And this is due to something called electronegativity. Electronegativity is the ability of an atom to attract the electron density, or the electron pair, from within a covalent bond. The factors that affect this ability are the nuclear charge of the atom and the distance between the nucleus of that atom and the pair of electrons that is being shared. You need to be reasonably swift at working out what the electronegativity will be of one atom or a pair of atoms, and so there are 2 patterns that you need to know. Firstly, as you work your way across a period, the electronegativity increases, and that's because the nuclear charge is increasing for the atom, and the distance between the nucleus and the shared pair of electrons is broadly the same, but in fact it's actually reducing a little bit because the atomic radius decreases as you work your way across the period. And so the electronegativity increases, except for the noble gases, because the noble gases don't typically form covalent bonds. And then the other pattern is, as you go up a group in the periodic table, the electronegativity increases. And that's because the distance between the nucleus and the shared pair of electrons is decreasing because each of the atoms has a smaller number of occupied energy levels as we go up. And so what that means is the most electronegative elements can be found at the top right of the periodic table, and the least electronegative elements will be found at the bottom left. When electron density is pulled closer to one atom than the other, this leads to a charge imbalance within that bond. And so, as I'm showing here, the atom on the left-hand side has had its electrons pulled slightly further away from it, and so it will be slightly positively charged, or we might say electron deficient. And the atom on the right-hand side here, the chlorine that has pulled the electrons closer to it, is going to end up being slightly negatively charged, or electron-rich. It can be quite complicated to show this with the electron cloud model as I'm showing here. And so what we typically do is we show the covalent bond as the traditional stick, but we acknowledge the slightly positive charge by using the Greek letter delta and putting a plus after it. And we actually say, instead of saying slightly positive or electron deficient, we can actually just write delta plus. And the chlorine is slightly negatively charged, and so again we use the delta minus symbol in this case. And in fact, in a question, if you're asked for the meaning of delta plus or delta minus, you can just say either electron deficient or electron rich, depending on which one they are asking you for. We would refer to this type of bond as being a polar bond because there is this charge imbalance. And we refer to the combination of the delta plus and the delta minus as a dipole, as in di for two, and pole as in there's a partial charge present. We should be clear that it's not the same as the ionic plus or minus, which is for a whole electron's worth of charge. This is smaller. This is a partial positive or a partial negative charge. It makes sense that if the electronegativity difference between two atoms gives rise to a dipole, that the larger the electronegativity difference is, the larger the dipole will be. And so at some point this dipole will become so large, the difference will become so large, that actually it stops being a partial positive charge and actually becomes a positive charge and a negative charge. And so it stops being a covalent bond and it becomes ionic. For A-level chemistry, you don't need to know the value where covalent becomes ionic, but it is taken to be an electronegativity difference of 1.7. And so, for instance, sodium has an electronegativity of 0.9, chlorine of 3.0, and so 2.1 is the difference between sodium and chloride, and so this will be ionic. But as I say, you don't need this precise number for A-level, just an appreciation of the concept that at some point the electronegativity difference becomes so big that the covalent substance becomes ionic. If a molecule has a polar bond in it, in other words a dipole, it's likely that that molecule will be polar overall. So for instance, if we consider HBr, the hydrogen will be electron deficient and the bromine will be electron rich because the bromine is more electronegative. And so this molecule will have a dipole and it will be polar overall. If we take a look at ammonia, nitrogen is very, very electronegative, and so it will pull electrons away from the three covalent bonds that it shares with hydrogen, and will have three dipoles within this molecule, and it will be polar overall, with the bottom part of this molecule being slightly positive and the top of the molecule being slightly negative. Whether or not a molecule is polar can have a really big impact on the strength of the attractions between neighbouring molecules, the intermolecular forces. And this in turn can affect so many things, for instance, the solubility of a molecule or its melting point and its boiling points. And I'm going to discuss this in further detail in a follow-up video to this one about intermolecular forces. It is possible that a molecule might have more than one dipole within its structure, but actually for it to be non-polar overall. And the reason for this is that this molecule will be almost totally symmetrical. And so what that means is the effects of the dipoles present within this molecule will cancel each other out. And so, for instance, if we take a look at carbon dioxide, The oxygen is significantly more electronegative than the carbon, so there will definitely be a dipole between each of the oxygens and the carbon in the centre. But because this is a linear molecule, these two dipoles will cancel each other out, and there will be no net dipole within this molecule. The same thing can be said of tetrachloromethane. The tetrahedral arrangement of the dipoles is such that each of these polar carbon to chlorine bonds is in an orientation that is cancelled out once the effects of these four dipoles are added together. And so again, this is a non-polar molecule. And the last example I'll use is BCl3. Boron is definitely less electronegative than chlorine, and so there will be a dipole for each of these molecules, and the polar bonds that are present will end up being non-polar because they are all in equal and opposite directions. A good way of thinking about this is by thinking about vectors. So if we take a look at the last example of BCl3, and we put a little dot in the centre here where the boron is, the first dipole is the one that I showed going to the right-hand side, and so we'll draw that as an arrow. If we take the one that was going up and left as my next arrow, and I'll connect it to the previous one, and then if I show the final arrow that was going down and left, and I connect that to my second arrow, what we find here is we end up back at the start, at that dot that I was at the beginning. And so this is a very nice way of proving that these three dipoles have cancelled each other out and their overall effect is zero, and we've got a non-polar molecule. Okay, that's the end of this video. Don't forget to check out my videos about intermolecular forces and shapes of molecules to build on these concepts. Hope it was useful. I'll see you again soon.